Improving the robustness of convolutional neural networks using inversion programming. Neural networks are not only used in computer science, but are applied to numerous applications today. These applications include self-driving cars, healthcare, and games. However, neural networks have their flaws. They provide you with state-of-the-art precision, but are susceptible to adversarial inputs. We want to know whether we can increase the robustness of a network using inversion programming. Our system consisted of 5 components: network generation, adversarial generation, inversion programming, robustness certification, and network testing. The goal of this was to create networks, which we then generated adversarial data for. We would then connect the network into an inversion setup and test to see if it was more robust than an individual network. This inversion setup was then distilled into a single network and fully tested again. The first component is network generation. Here is an example of me creating 3 different networks. You can see me typing network 1, network 2, and network 3. Each network is trained and saved. The next component is adversarial generation. We can visualize what the data looks like by running the command where we give the network name and the attack type. Here is a visualization of all the attacks we tried. SLSQP attack was rejected as humans would be able to identify this as an adversarial attack. Next, we generate the dataset by giving this Python script all the networks we want to include in our dataset. It combines all the images into a single dataset. We can see what all the data looks like by inspecting the output. Here we can see that the original label was 9, but the adversarial label was 8. We now wanted to see if inversion programming did indeed increase the robustness of our network. We did this by giving this script all the networks we wanted to include. The script then took the adversarial data we just generated and passed it to each of the individual networks. It then connected the networks into an inversion setup, increasing n incrementally while recording how the system did on the adversarial data. We can see that none of the individual networks was able to achieve an accuracy greater than 65%. However, when connected to a voter, they were able to achieve an accuracy of 90%. Next, we distilled the inversion setup into a single network. We can see the single network being trained here. The final part of our project was to test this network to see if we were able to maintain the robustness from the inversion setup. To do this, we passed both the MNIST testing dataset as well as our adversarial dataset to all the individual networks as well as our distilled network. Inspection of the data shows that all networks perform well on the MNIST test dataset. However, when we look at the adversarial accuracy, network 1 gets 50%, network 2 gets 60%, network 3 gets 60%, while our distilled network gets a 90% accuracy. This leads us to believe that it is possible to increase the robustness of a network using inversion programming.